let's get started. Thanks everyone for coming. My name is Brian, and I'm here with Louis today. We're both software engineers on the front-end infrastructure team at Coursera. And today we're going to walk you through a couple different problems that we found around site performance, reliability, and developer productivity. And then how we've leveraged different tools and technologies from AWS to help us solve these problems. But before I get into that, I want to just give a quick overview of Coursera. Actually, I'm curious, maybe show of hands, how many of you have actually taken a course on Coursera before? Oh, whoa, that's a lot of people. That's awesome. So for those of you who aren't familiar, Coursera is an online education platform. And we envision a world where anyone, anywhere can transform their life by accessing the world's best learning experience. And we've been around for about 5 or 6 years now. And over that time, we've had actually over 30 million learners register on our platform. And we've partnered with over 150 different partners, both the top universities in the world, as well as some leading industry partners. And together, we've worked with them to create over 2,200 courses that we make available to all of our learners. And one thing that I'm really proud about is that 70% of those 30 million learners actually come from outside of the United States. So we have really a worldwide audience. And over that time, we've grown the platform a lot, but we've also grown a lot as a company, too. So actually, last time I checked, I saw that we have over 70 engineers working at Coursera. And that's a lot of people, but there's a lot of work to do in order to build this world-class platform. And Louis and I, we're on the front-end infrastructure team. So on that team, we actually have kind of 2 different goals. The first one is to keep Coursera's site as fast and reliable as possible. But the other one is to empower Coursera's engineers, especially our front-end engineers, to be as productive and as efficient as possible. So over the next 45 minutes or so, we're going to walk you through a couple different stories of problems that we've faced, and then different tools and technologies from AWS that we've used to help solve these problems. So Louis is going to kick things off by discussing some problems that we faced with our build tooling.
All right, thanks, Brian. So before I really get into CodeBuild, I just wanted to kind of go over one thing that Brian mentioned about productivity, right? Something that we look to do is optimize productivity, and we found that actually productivity at Coursera increases when we decrease the time between when a code commit goes in and when the deploy goes out. And we recently used CodeBuild to make this process better, but before I kind of go into CodeBuild itself, I wanted to walk you through the problem that we were actually facing at Coursera. So at Coursera, we have always treated our backend and frontend as separate kind of code entities, right? Our backend was always organized as microservices, and honestly, that worked really well for us, and that kind of stood the test of time very well. So I'm not going to talk about that today. What I want to talk about actually is our frontend. In 2013, instead of having our front-end code split up like you would in a microservices architecture, our front-end code base was actually organized as a monolith. And this wasn't something that happened on purpose. It just kind of happened that way, right? We started with JavaScript code for one page, and as we added more and more products, we just kept adding those pages to the same code base. And so in 2013, we had a monolith where if a developer changed any of the JavaScript code for Coursera, we would rebuild and redeploy all the JavaScript code for our front end. But this was fine, right? Because in 2013, we didn't have that much JavaScript code. And so the time after committing, commit to build to deploy, that all just took 5 minutes. And so developers could actually treat commit and deploy as a single task. And what we saw from that was that with really granular deploys, regression debugging was really easy because we could just look at our error monitors or look at the time someone reports a regression and then match up that with when our deploy events actually happened. And then we could figure out exactly what code change caused the regression. But with this approach, at the time, we didn't ask if that would actually scale, right? This process actually didn't scale. As we hired more developers, built more products, and increased the size of our front-end monolith, our builds went from 5 minutes to 15 to 30 minutes. Now, in Coursera in 2016, the builds were taking over 30 minutes. And as a result of that, developers could no longer treat commit and deploy as a single task. And so they would actually end up switching to another task and sometimes forgetting to actually deploy. And as a result of that, actually, we had deploys that would go out with 10, 15, 20 different commits. And so if we actually wanted to have the regression debugging process that we had before, it just wouldn't work. We had to actually go in, investigate the deploy, see what commits went out with that, and actually look at every single code change within that deploy. Increasing build times wasn't the only problem that we had with the monolith. Because we treated our monolith as a single unit to build and deploy, we saw that sometimes when one bad commit caused a bug on master, it would actually stop all the developers from deploying. Right? So here's an example. Say we have 5 commits that landed kind of within the same time of each other. The first 2 are fine. So we actually go ahead and deploy those changes. During testing, however, we discovered that the 3rd commit actually introduces a regression. For instance, let's say that commit caused a lecture video player to default to playing stuff at 2x speed. And that's not something that we actually want all our users doing, unless they actually desire it. So we don't want to deploy this. But let's say after this commit goes in, another commit comes in where we actually want to update the terms of use page, and our legal team wants it out as soon as possible. If we actually deploy this change, though, we would deploy that video regression too, right? Even though the video player and the terms of use page are completely different parts of our site. So with these problems in mind, we decided that we had to take our front-end monolith and split it up. Right? And in order to do that, we did 2 things. We actually decided to treat every single application as its own buildable unit. And so instead of a build script saying, let's just build all the things that we see that look like front-end code, we would have a script that was parameterized by application so that we could actually build individual applications. Another thing that we did was we added a source-based dependency analysis so that we could take a look at it. We could take a code change and then inspect it and figure out the minimal number of applications that we had to build. With these 2 changes in harmony, whenever a developer landed a code change, instead of kicking off a monolithic build for the whole repository, we would only kick off the builds for singular applications that were affected. And this was the result. Say, for instance, we have a bug fix that comes in for the learning plans application. We would only really need to build this app, right? Our dependency resolution system that we had built would figure out that this is the only application that needs to get built. In another case where, let's say there's a code change to a UI component that's being used by 3 of our applications, we would only have to build those 3 applications. So in both of these cases, we've kind of succeeded. We've sped up our build times by building less code, and we've also separated the build and deploy process for all of the different applications. But we weren't done yet, right? Because at worst case, a component that all of our applications use, like our page header, could be changed, and then we'd have to actually build and deploy all of our applications at that moment. And what happened with this is that we actually saw that we still had issues, right? And these issues came because for our build system at the time, we were using Jenkins. And it isn't necessarily the fault of Jenkins itself, but how we were using Jenkins. We kept a pool of workers on EC2, and we set up an auto-scaling configuration that would approximate the capacity needed to work through our build queue during the day without it getting too backed up. Right? And I think this is fairly standard what people do with Jenkins. So at night, you might get away with just 2 workers, but during the day, we would scale up, right? And at the time, we set a max limit of 8 workers because we wanted to be cost-conscious. Now, 8 workers definitely is not enough if a code commit could suddenly trigger 50 different builds and add those to the build queue, right? So what we saw was that when 50 builds landed in the build queue, the 8 workers would pick up 8 builds, take 5 minutes to churn through those builds, pick up another 8 builds, and each time it does this, it'd be 5-minute increments, eventually finishing everything, right? But the problem is, it would take 35 minutes in this case to actually produce a full build, right? So we're back to square one. We haven't really improved our build time at all. But we knew that we wanted to go from nothing being built to everything being built within 5 minutes. And the way to do that was that we needed to have access to n workers, where n is the number of applications that need to be built, from the moment that a code change, in the worst case scenario, lands. So at first we said, OK, can we automatically scale our Jenkins worker pool quick enough to do this? And as we tried this, we found that it was too slow to boot up these EC2 instances to support the bursty build behavior that we were seeing. The next thing we thought of is, can we actually over-provision Jenkins? Unfortunately, that isn't cost effective because then you might have a lot of idle workers sitting around that you're paying for that aren't doing anything. But to make matters worse, right, multiple commits might actually land minutes from each other. And we've actually seen this happen pretty often. We had an example where a growth team needed to land commits for a feature that they're working on in time for a demo session. And so maybe they needed to update the page header, then add links to a footer, and update a button component to support some things needed for that feature. When these code commits land, we actually saw that we would have over 100 builds suddenly queued up in our build system. And so 8 workers churning through this would take a really long time. That was just something that we couldn't do. So that's when we asked ourselves, can we do better? Is there something we can do to make sure that we can actually trigger all these builds from the beginning and work through them all at the same time? And that's when we turned to CodeBuild. And for those of you who haven't used CodeBuild before, or maybe have only heard a little bit about it, I wanted to give a quick overview of what it is. CodeBuild is a fully managed build service that AWS launched late last year. It provides on-demand build resources. So you don't have to actually reserve build resources. You don't have to have them sitting around. The moment you trigger a build, CodeBuild will provide resources for you. In addition to that, all of this happens inside a Docker container. So you get fresh environments every time, so you don't have to maintain your build systems. And there's also near infinite elastic capacity, right? So you basically get as much as you're willing to pay for. Now, I have to caveat that with, by default, I believe that you can have 20 concurrent builds running at the same time. But that's something that you can reach out to AWS support for if you want to trigger more than 20 builds concurrently. Another thing about CodeBuild that we really like is the pricing model. They charge per build minute. So you're really only ever paying for what you need. You're not paying for idle resources. You're not paying for idle resources. And so if we wanted to go from nothing being built to everything being built within 5 minutes, that was really good, right? Because we didn't have to pay for instances that were sitting around before and after the build. In the case of that example with the growth team, everything would happen in 5 minutes as well, and we'd pay for only the resources that we need. So some of you might be wondering, like, what was the process of migrating from Jenkins to CodeBuild? And I'm not going to go into this in too much detail, but I can just say in our experience, it was actually relatively easy. We were able to take our build scripts that we were running on Jenkins and make some minor modifications to get it to run on CodeBuild. And those modifications were to just make it compliant with what CodeBuild expects. Right? So I would definitely recommend checking out the documentation because it's very concise and it explains to you how you can set up an optimal build environment and also set up a build specification. Cool. So another thing that we realized once we moved to CodeBuild was that the optimization problem for our build processes changed almost entirely. Instead of thinking about how do we actually auto-scale our worker pool effectively, we could start thinking about how do we optimize the slowest individual build time? Because if you're parallelizing all your build tasks, then the slowest thing is the weakest link. So now we can just think about taking the slowest process, figure out why it's inefficient, and then optimizing that. I wanted to go through a couple of tips and tricks. These are things that we kind of learned along the way. The first thing is build visualization. So CodeBuild is just a generalized build runner. In our case, there is actually a relationship between a code commit and the different builds that it triggered. So we actually built a visualization for our developers that kind of showed that off. Something else that we did was we supercharged our logs. Because CodeBuild build logs are actually hooked up to CloudWatch, and it's very easy to set up third-party integrations between CloudWatch and other services, we actually now funnel all of our CodeBuild logs to Sumo Logic, so our developers can use Sumo Logic's powerful search operators to debug their own build issues. The last thing that I wanted to mention was that there is a AWS CodeBuild Jenkins plugin. So if your thought is CodeBuild sounds great, but it might be a lot of work to move off Jenkins, you can actually now, using this plugin, use CodeBuild to work through your build queue on Jenkins. So I definitely recommend checking that out. Cool. So next, Brian is going to talk a little bit about how we use EC2 Container Service.
Thanks, Lewis. So now I'll talk a little bit about how we actually use EC2 Container Service to make our site a little bit more reliable. But before I go too far into this, let's just go over a little bit of context and history first. So Coursera's entire website is built using a single-page application architecture. We dynamically render our entire page using JavaScript and React. And this is a really great way to separate concerns. It makes our front-end developers much happier and much more efficient, but it can come with a little bit of a performance cost. That's because when you first load a page on Coursera, at least if you did this like a year or two ago, you wouldn't actually get this beautiful homepage here. You'd see something that looks a little bit like this. And that's because when you first load the page, we don't actually have any content in there. We just have a link to JavaScript files that we need to render the page. So what your browser will do, it'll go download that JavaScript file, and then it'll start rendering the page. And then you'll probably get something that looks like this. You'll probably get the header bar in there or something. But now what your browser needs to do is go make some API calls and fetch the data that it needs to render the rest of the page. And then finally, we'll make those API calls, get the data back, and then be able to render our full page. But this is a really crappy user experience. Just imagine someone telling you about Coursera and going to our site for the first time and waiting 20 seconds for the page to load. I mean, no one's actually going to do that. If it was me, I'd probably wait 5 seconds and then go watch some cat videos on Reddit instead. And that was just Reddit's cool and everything, but we really want to be able to transform lives and let people learn skills like machine learning or accounting on Coursera. So we need to fix this problem. But one problem we had is that our entire site is rendered using this single-page application architecture. And we couldn't throw away 5 years' worth of code and start over, start doing things on the server. So we embraced a technique referred to as server-side rendering in React, which basically allows us to execute Node.js on the server and make all of these API calls on the server, and then send fully rendered HTML to the client. So on the left here is kind of that skeleton page that we had before, where we'd send the HTML to the browser with just a link to JavaScript and a loading indicator. And then the browser would go execute everything. But on the right, this is a slightly truncated example of what you'll see if you actually use server-side rendering to send the full content and the full HTML to the client. And this means that once the browser gets this HTML, it's able to render it immediately, instead of having to go download the JavaScript and then make API calls to get all that data. So we wanted to build this service to render these pages. And I'll admit, we're not the most creative people when it comes to naming things. We have a user service, we have an authentication service, and a payment service. So we need to build a service for rendering pages. And you can probably guess, we called it the render service. But what we lack in naming creativity, I think we make up for in expertise in running Scala services. We run like 50 or 60 of them now, and we've gotten pretty good at it. We know how to deploy them, we can monitor them, we know all the tuning and everything that we need to do. We got all that pretty much taken care of. And we didn't want to build a new service in like Node.js or something and launch that into our infrastructure, because that would be a lot to maintain and manage. So we made this service a Scala service. But unfortunately, Scala can't really execute JavaScript. But Node.js is really good at that. So we took the Scala service, and we just added some Node.js to it. We basically set up a Node.js code process to run alongside the Scala service, with the Node.js executing the JavaScript and the Scala part doing everything else. But this Node.js part acts a little bit differently than the Scala part. As Lewis mentioned before, our commit to deploy process is very streamlined. We could have people deploying code within 5 minutes of committing it. But for our Scala services, the deploys typically take a little bit longer because there's a bit more in that process. We we have to compile the code, build Debian packages, upload them, launch EC2 instances, install the Debian package, wait for it to health check, and then slowly shift traffic over. And that whole process can take like 20 or 30 minutes. So in order to keep our deploys really fast for our JavaScript part, we added in a dynamic way to update that Node.js part. So on every JavaScript deploy, we'll download a new version of the JavaScript. And then we'll use blue-green deployments, and we'll slowly shift traffic over from the old version to the new version. And then after we shift to 100%, we'll clean things up. And this we do entirely without actually launching any new EC2 instances. And this actually worked out really well for us. But just like Lewis mentioned earlier, when we ran into a problem once we split up all of our applications and the builds took much longer, we began to see some problems in this render service too. Because now there wasn't just one version of code that we were running. There were like 50 or 60. And it made a lot of things like asset downloading and shifting traffic over and cleaning up much more complicated. But we also ran into a couple of weird situations too, as a result from the multi-tenancy that we had here, basically where we were running all of these applications on a single host. So every once in a while, one of our applications is going to break. There could be like a buggy deploy that someone commits, maybe one of our backend services breaks or slows down, database has an issue, or maybe even some third party that we depend on breaks. And we've kind of accepted that we're never actually going to have 100% uptime. Instead, we really just want to optimize for finding and fixing the problem as quickly as possible and keeping all of our problems as contained as possible. We don't want, if one application breaks or someone deploys one code in one bad application that's buggy, we don't want that to affect the rest of Coursera. But what we saw in this case is that actually was the problem, where errors in one application could actually bleed over into other applications and cause the entire site to slow down. And this is because we actually use a shared node worker pool with all of these applications. So if one application slowed down or started using a lot of CPU, it could cause all of the other applications to get backed up or crash, or there could be random errors between them. And this was really a problem that we couldn't live with. So we tried to figure out some other solutions for how to really make sure that an error in one application didn't bleed over to the others. So we brainstormed some different things, and we came up with a couple different ideas. And the first one we thought about was basically just going to the extreme other end. Instead of running all of our applications on a single host, what if we just took every application and put it in its own EC2 instance? And this would actually probably work pretty well for us. But we'd still have to figure out how to do the dynamic asset downloading. But I'll be completely honest, when we were thinking about this approach, we estimated some costs for this, and we saw that it would end up costing about like 5 or 10 times as much money as running everything on a single host. Especially because a lot of our applications are, maybe they get little traffic or they're internal use only, and we didn't want the overhead of running an EC2 instance for all of those applications too. So we kept brainstorming, and we found another solution that I think worked out pretty well for us. And it came in the form of containers, using the EC2 container service. And this really gives us the best of both worlds. We get the multi-tenancy that we need to keep our costs down by being able to run all of these containers on a single host, but it also gives us that isolation to make sure that if one application breaks, it doesn't take down the rest of Coursera. But before we go too far into this, let's just go over quickly a little bit more about ECS. So at its heart, ECS is basically a container management or orchestration system. So this means that you just tell it what you want it to do. For instance, take these containers and run them across these hosts, and it'll do it all for you. And it really hides a lot of that complexity around managing Docker and distributing tasks behind a really nice API. But under the hood, though, it's actually just running all of these containers on just EC2 instances that are running the ECS agent. So this means that you're not actually losing any control over things. You're able to SSH into the machine. You could run it using your own AMI, run any arbitrary applications, like monitoring applications on there. And anything else that you could do with EC2, you're able to do with these ECS hosts also. But while this does give you a lot of control, ECS is really able to manage a lot of this for you. So it could help you with auto-scaling. You could set up a couple of rules saying, if maybe CPU usage on these containers goes above a certain threshold, add more containers. It could also handle dynamic resource reservations. So you could include, along with each container specification, how much CPU and how much memory you want it to have. And ECS will make sure that that container has always at least that amount of memory. It could always go more if there's more on the host, but it makes sure that that amount of memory or CPU is always available to that container. It also can handle health checking for you. So you could set up a couple different rules and say, if some container ever dies or stops responding to health checks or something, just kill that container and launch a new one. And then a new one will launch normally within seconds. And lastly, as I mentioned earlier, these are all really complicated processes under the hood. But ECS hides all of that away behind some really nice APIs that make it really easy to do everything that you need to do. So switching to ECS for us was actually pretty easy. We took those CodeBuild jobs that Louis mentioned earlier, and then had them export a Docker image with those assets that we built in there, and uploaded it to the EC2 container registry. And then when a user wanted to deploy, we just took our existing deployment pipeline and made some API calls to ECS to launch a service, register with the auto-scaling group, and then slowly shift traffic over to that new version. And there honestly wasn't anything too unique or special about our approach with moving to ECS. Everything that we did was pretty much straight out of the AWS documentation and all those guides, and that really just kind of covered everything that we needed to do. So I don't want to go into those details too much. But what I do want to discuss is some of the results that we saw and some tips and tricks that we learned from this. So the first thing that I want to point out is that we saw that our pages were actually being served 30% faster than they used to once we switched to ECS. I think one of the reasons for this is that extra isolation that we had between all of our different applications. Because we were using the shared node workers before, we would have some problems where they would parse JavaScript files for one application and then go start serving requests to another application, and then they would garbage collect those original application files. And then that extra overhead of having to parse those JavaScript files over and over again was really adding up. But now that we had our JavaScript files bundled into our container, and each node worker was only responsible for one application, they were just running much more efficiently. We also saw a lot of benefits from being able to scale containers much more quickly. So we're running all these things on our EC2 hosts, and we generally leave a little bit of extra capacity along with all of our hosts. So if we ever need to scale one application up, we had some room for that there. And every once in a while, some certain part of Coursera site normally gets, or sometimes gets some rapid influx of traffic, such as the time that Oprah tweeted to her millions of followers about the Coursera course that she really liked. And in these instances, we needed to make sure that Coursera didn't go down. We definitely didn't want to disappoint Oprah. So we needed to find a way to make sure that we could scale up, maybe double or triple the amount of traffic that we were getting before, without actually going down or causing any problems or anything. But before we were running on ECS, with those EC2 instances, we saw that if we needed to scale up, it would take like 5 or so minutes for us to launch those new EC2 instances and get them fully ready. And if we waited 5 minutes while our traffic was doubling, that could actually cause some outages on Coursera. So the other approach that we took was to basically run everything in a very over-provisioned state. We ran like 2 or 3 times as much capacity as we needed, just to make sure when we got those sudden bursts that we were able to handle the load. But this ended up costing us a lot of extra money. But with ECS, we're able to run much closer to the capacity that we actually need at any given time, because we're able to scale up and launch new containers within seconds instead of minutes. But I'll be honest, all of these things are really cool, and everyone is really happy that we're saving money and things were faster. But this wasn't actually the main reason that we switched to ECS in the first place. The main reason was to make sure that if one application broke, it didn't cause other parts of Coursera to go down. But I'm really happy to say that we actually did solve that problem too. So I pulled this graph from a recent outage, I guess, that we had. I pulled this from Datadog, and you can see each of the blue lines here represents the latency from one of our applications. And around 7:30 or so, I think it was one of our backend services that started just slowing down a lot. And we can see that the front-end application also slowed down a lot there. But only one application slowed down. Every other application kept working just as they were before. And they didn't know that there was any problem going on. So we were really happy that we did solve this problem and made sure that if there is some problem that happens, it's contained to just the one application that it affects. And one last thing that I want to point out about this project is that it was honestly actually pretty easy to do. It only took one developer about 2 months or so to migrate everything over. And this involved writing a whole bunch of documentation also and writing nice guides and building a nice UI for everything. Honestly, the ECS APIs, we just kind of plugged them in where we were launching things before, and everything just pretty much worked for us. So it doesn't take too much investment at all to move to ECS, but I'll say that there were a couple decisions or some things that we learned along the way that I want to just share with all of you. One thing that you want to think about is how to scale your containers and your hosts. So I'd really recommend for your containers to just pick a single metric that you want to scale on. Pick either CPU usage or memory usage, and figure out which one you're most bound by as your traffic increases, and just scale by that. Don't overcomplicate things too much on your containers. But for your ECS host, sometimes picking just one metric isn't enough, especially because these containers can have reservations for CPU and memory usage. So you might see that you're launching 5 containers that each use or have a reservation for 1/5 of the memory on the host. But in reality, they're only actually using maybe a quarter of what they're reserving. So if you're trying to scale based on memory, in that case, the memory usage might only be 25%, but if you tried to launch a new container, there wouldn't actually be any room on the host. So I actually found this great blog post that kind of describes a different way to scale your ECS hosts. And it works by computing a new metric that basically asks at any given time, how many new containers can I launch on this host? So it looks at the highest memory reservation and CPU reservation, and looks at how much is available on your host, and then basically computes the number of new containers you can launch at any given time. And then you can use that number to scale up or down accordingly. Additionally, you'll want to try to find a way to automate your deployments. So we ended up building kind of a homegrown system that managed our whole deployment. But there's a lot of other great utilities, such as Code Deploy or CloudFormation, that are able to manage your deployments for you. You probably don't want to go into the console every time and click a whole bunch of buttons to launch new things. So these tools can actually kind of automate that entire process. And then they even let you use blue-green deployments, so you can launch new containers, then slowly shift traffic over, and then delete the old ones. So there's another great blog post here that kind of describes how to do that. It has some code samples there, too. Another thing that we learned, when we first created our containers, we basically made each of them a mini replica of what we were running on EC2. So we had our application in there, but we also had some extra utilities such as log monitoring and collection, metrics collection, and some security tools in there too. But we found that this made our containers very heavyweight, and it took them a while to launch and health check and everything, and it seemed a little excessive. So one technique that we read about and actually implemented was to take all of these extra utilities and pull them out to their own containers, and then share those amongst all the different containers on the host. So for instance, we're using Sumo Logic, and we have a log collector on there. But we don't need a different log collector for each of our containers. They can all just forward their logs to that one container running on the host, and that works fine. So that keeps our containers much smaller, and they're able to launch much more quickly. And one last thing that I want to leave you with about ECS, you're probably going to have a lot of different options in how to actually size your containers. So you might want to run fewer containers that have larger usage or larger reservations, or you could have more containers that are a bit smaller. Honestly, there's no great answer here. There's no one way to do it. I'd really just recommend kind of experimenting, doing some load tests, see how quickly things boot up, and figure out which one works best for your application architecture. And honestly, I think this overall theme is kind of the approach that we took with ECS. Just try things out and experiment with it and see if it works for you. We didn't go into this project knowing that we definitely wanted to use ECS for this. We experimented, we launched a few containers, we ran some load tests, and saw how things worked for us, and saw that ECS was a good option for us. So I'd really encourage you to just kind of give ECS a try and see how well it works for you. Next, Lewis is going to talk a little bit about how we put everything together with the application load balancer.
Cool. So earlier, I kind of walked through how we build applications with CodeBuild, and then Brian just kind of demonstrated how we run things with ECS. But there's one more thing that we need to do. Oh, sorry. All right. So there's one more thing that we actually need to do. We need to actually route requests to different URLs on Coursera.org to the actual applications running in ECS. Right? So for instance, if one of our users wants to view the catalog and goes to Coursera.org/browse, we need to make sure that request actually gets to the catalog application running in ECS. So we actually knew that with our application running ECS, we needed a load balancer, and that combined with the whole need of needing to actually route these requests coming to production, we were actually able to satisfy these needs using application load balancer. And since application load balancer is quite the mouthful, I'm going to start referring to it as ALB for short. So quick overview of ALB. ALB is actually, it sounds familiar, but it's actually a relatively new load balancer product that launched last year, I believe in August 2016. And it is part of the ELB ecosystem. So I wanted to just give a quick overview, just in case. Just like classic load balancer, ALB is able to distribute traffic across multiple targets in different target groups in different AZs. It provides support for load balancing containers in ECS, and this is something that classic load balancer did not support. And so for us, using ECS, this was a no-brainer. We had to use this. But ALB also comes with an interesting feature called content-based routing. And it does this via listener rules. And what content-based routing is that it's actually able to look at the content of the request, or at least some parts of the content of the request, and figure out from that information where that request should go. And right now, there are two different methods available. There's path-based routing, where you're actually able to inspect the URL and figure out where this request should go. And there's host-based routing, where you inspect the host field, the host HTTP header, to figure out where to route incoming requests. And so you have to set up listener rules, right? The listener rules are the things that are able to match up the host header or the path with where a request should go. Fortunately, setting up these listener rules is really easy to do. You can do these via the AWS SDK or via the CLI. And we actually set up these listener rules when we actually boot up our applications in ECS. OK, so that's a quick ALB overview. Back to the problem at hand. So we have many different applications running in ECS. How do we actually route requests to the correct applications? So our first thought here was maybe we should use path-based routing, right? Because there's a pretty good mapping of the path that a user is visiting to which application should go to. But as we started to try this out, we realized that path-based routing was actually a little bit too limited, right? Because things like authentication can affect routing, maybe experiments, maybe for one user who's in variant A, you want to send them to one application. For a user in variant B, you want to send them to another application. And we've actually seen this happen where our growth team was trying to roll out a new onboarding experience, and they wanted to compare the conversion rate between the old onboarding experience and the new onboarding experience. So we actually do routing based on experimental variant. So we actually started looking at host-based routing, and what we realized is that this can actually be really flexible, right? And it can be flexible if you're able to actually intercept the request in an edge tier and generate your own host header. And so that's actually what we did at Coursera, right? We had the request that come in, hit the edge tier first. The edge tier would be able to talk to our authentication service and our experiment service and any other service it needs to talk to figure out or to gather the information it needs to determine where the request should go. It would compile that information and generate a proper host header that ALB would then be able to recognize to redirect the request to the correct set of containers. For our host headers, the way we approached it was we basically concatenated the application name with like a version hash, right? And that version hash was just a hash that uniquely identified the build. So after we generate that host header, we would forward that to ALB. Remember, we have already set up listener rules on ALB, so ALB will be able to figure out, OK, this host header is something that I recognize. I'm going to forward this request along to the proper target. And so then we'd have a bunch of targets that are ready to accept this request. More concretely, in the example of the catalog, if a user hits our site trying to visit the browse page, Edge would generate a host header, in this case catalog-A328Z2F, which is the version. So forward that along to ALB, and ALB would know how to actually forward this request along to our catalog cluster running in ECS. So we're done here, right? We've set up routing for our production services, but there's something else that our developers are asking for. Our developers actually wanted to be able to preview changes that they were working on in a production-like environment, so kind of like a staging environment. So we wanted to see if this was possible to do with ALB. So we looked into a little bit more, and we noticed that, OK, so we already have our catalog cluster running in ALB. Let's say 2 developers, Alice and Bob, are both working on catalog features. Alice has 2 branches, catalog feature A1 and catalog feature A2, and Bob has catalog feature B1, feature B2. So what we realized was that just by changing our build process to trigger on pull requests as well, we could then spin up containers running development branch code side by side with their production clusters. And then when we go back to this picture, we're able to then by default, even though when Alice requests the catalog page, we get the production version, she's actually able to specify an override. So she can ask for catalog ZXW, and again, Edge would generate the proper host header for that to ALB, and then ALB would then be able to redirect that to her preview build. Bob can do the same thing and request BZ4, and throughout this whole process, he would be able to view his changes. And they can toggle between these pretty easily, right? If you set up an override via like a cookie or a header, and the Edge tier understands that, then it's something that they can just switch very quickly in their browsers using some development tools. So this was really cool because we were able to use ALB to do something that maybe it wasn't necessarily designed for, but through it, we were actually able to set up a staging environment. But there are some limitations that I want to make you guys kind of aware of. Actually, one of the limitations that we ran into was that the max number of listener rules you can set up in ALB is 100. And given that we have 50 apps, and we might want to have a bunch of preview builds for these, our listener rules could quickly get out of hand. So we had to actually clean these up as we were going along. And there are other kind of hard limits that exist. I would recommend checking the documentation if you're looking to design kind of a solution like we have here, and just make sure that your solution works well within these limitations. Another limitation that we ran into was that we do blue-green deployments, and something that we want to be able to do is slowly shift traffic from an older version to a new version. But ALB does not support traffic waiting out of the box. Fortunately for us, this was actually pretty easy for us to implement in our Edge tier. So that's just something to keep in mind if you guys are looking to do something very similar. And so that's all I got for ALB. Brian's going to do a quick recap of what we went over today.
Thanks. Yeah, so we have a decent amount of time left. We'll have some time for questions after. But just real quickly, kind of what we went over today. So as Louis first mentioned, you can really use AWS CodeBuild to scale your build environment on demand. And we really like the pricing model here where you're only paying for what you're actually using. You don't have to worry about idle instances sitting around costing you money. You can really take advantage of this elasticity. Then we spoke a little bit about ECS and how it really lets you keep all of your applications independent without having to worry about problems with multi-tenancy, but it also keeps the cost down by letting you run a lot of things on a single EC2 host. And you're able to scale a lot faster, too. And lastly, Louis just mentioned how ALBs can be used in a lot of different creative ways to maybe build staging environments or some other cool ideas that you have for different creative ways to route things. So that's actually all that we have now. We have a decent amount of time. If anyone has questions, maybe we'll ask them here now, and then we'll be over here later to talk a little bit more. Thanks, everyone.